Okay, last, alpha strongly convex and beta smooth case. Let's go back to the unconstrained case when f is alpha strongly convex and beta smooth. From the vanilla analysis, we have this. And also from alpha strongly convex, we have this inequality. So that was the two main ingredients to show the linear convergence speed, the exponentially fast convergence. So when we set gamma equal to 1 over beta, so when we set the step size equal to 1 over beta, from the two fact, we have xt plus 1 minus x star normed square is less than or equal to 1 minus alpha over beta xt minus x star normed square. So we can very easily show the distance to the optimal point x star is exponentially decrease as we increase the number of iterations. But again, we cannot directly use these properties. First of all, very important thing is we cannot use this because xt plus 1 is not the gradient update anymore. Xt plus 1 can be the projected point for yt plus 1. So we first update yt plus 1 using the gradient descent, and we have to project yt plus 1 so that the next point also can be inside the constraint set. The next point can satisfy your constraint. Okay, so so we have to deal with the projection. So now we have this inequality. Okay, so this one comes from the proof of Lipschitz continuous case. In that case, when we show the convergence of Lipschitz continuous case with constraint set, we reformulate the vanilla analysis, and at that time we have this additional term minus 1 over 2 gamma, the norm of yt plus 1 minus xt plus 1 square. So that was the additional thing. So previously we don't have such term, so we have this additional term. Next one, we have inequality instead of equality. But fortunately, this inequality sign doesn't matter because we always want to upper bound thing. Okay. And also this side, we have a lower bound, and this side can be this. Okay. Even if we replace this equality using this sign, all the remaining result still hold. So this is okay, fortunately. And actually that's why the Lipschitz continuous case with constraint set, convex constraint set, we can still have the same convergence speed, 1 over square root of t. Okay. So from the vanilla analysis, we have this. And the projected gradient descent algorithm has this property. Xt plus 1 minus x star norm square is less than or equal to 2 over beta fx star minus fxt plus 1 over beta square gradient of fxt norm square minus fyt plus 1 minus xt plus 1 norm square plus 1 minus alpha over beta xt minus x star norm square. How to obtain this inequality? Simple. I first use this inequality, and then I will use Another inequality comes from the definition of alpha strongly convex, which is this. We have this row bound, and this row bound always hold as long as xt and x star in the constraint set, and we have a strong convex function. So here we use the alpha strongly convex property and this one. So in the end, we have this first inequality. And then I use this fact, fx star minus fxt is less than or equal to fxt plus 1 minus fxt, because fx star is the optimal point. And from page 11, let's go back to page 11. We have this sufficient decrease property we obtain, which basically this one is the same as before, but we have this additional term for this sufficient decrease. And this additional term, fortunately, can remove this part. Okay, very interesting. So in the end, we have this inequality, xt plus 1 minus x star square is less than or equal to 1 minus alpha over beta times xt minus x star norm square.